Welcome back to the Deep Dive, where we tear apart complex source material to give you the essential insights, the blueprint for success.
Today, we are really strapping in for an industrial engineering challenge that's, well, it's massive, it's unforgiving, and it's absolutely crucial for the green transition.
We're talking about electrifying heavy construction.
Specifically, we're looking at the P2 hybrid cement mixer truck. And this isn't about the main truck engine. It's all about the 400-volt electric upper structure, the ePTO system, that actually powers the mixing drum.
And that system has to do everything. It needs immense torque, it has to work flawlessly in, chaotic environments.
And deliver perfect concrete, all while cutting costs. It's a huge ask.
It really is. And what we have in front of us looks like an internal engineering playbook. This is a full consultancy-style report, the kind designed to take a company from just a concept all the way to market leader.
The mission it lays out is ruthlessly clear.
Which is?
To build a world-class testing and validation capability from the ground up. The goal is simple, but incredibly hard to achieve. Go on. This new electric system has to surpass its traditional, noisy, hydraulic predecessor in every single measurable way. Quality, reliability, safety. Everything.
No half measures.
None. The stakes are just too high. If these electric mixers fail in the field, if one breaks down on a steep hill or ruins a batch of concrete, it could set back the whole heavy-duty EV trend by years.
So to prevent that, the source material defines success using this framework they call the pentagram of performance.
Right. It's a framework with 5 non-negotiable dimensions. The whole validation process is built around these 5 points.
The 5 pillars of industrial viability. If you fail one, the whole program fails.
Pretty much.
Okay, walk us through them. What are these non-negotiables?
So they're chosen to cover every risk and every opportunity. First up is energy efficiency. That's the main driver for total cost of ownership, TCO.
The money metric.
Exactly. Second, mixing performance. This is your core product quality. You cannot compromise the concrete. Third is extreme conditions, proving the system is robust in the absolute worst-case scenarios.
Things a construction site can definitely throw at it.
Oh, yeah. Fourth, NVH and comfort. That's the user experience, and it's a huge untapped market advantage. And finally, number 5, safety and compliance.
And this isn't just basic safety.
No, we're talking about hitting the highest automotive standards, like ISO 26262 for functional safety. And we're going to get into the precise data thresholds for every single one of these.
So let's start at the very beginning with the foundation, getting reliable data. Why does testing for a cement mixer have to be so incredibly standardized? You're just rotating a drum. How complicated can it really be?
Well, the complexity isn't the drum itself. It's the environment it's in and the stuff it's holding.
The concrete.
The concrete. It's a non-Newtonian fluid. Its viscosity changes based on temperature, moisture, how long it's been agitated.
Right.
And on top of that, construction sites are, completely uncontrolled. You could be driving through a desert at 45 degrees Celsius, then park on a muddy, steep incline, all in the same trip.
So any data you collect in the real world is just inherently too messy to draw solid engineering conclusions from.
Exactly. If your testing isn't repeatable and comparable, your data is basically garbage, and you can't make valid engineering changes. The source material, it calls the testing framework, the DV and PV process, the absolute firewall against systemic failure in mass production.
A firewall. I like that. You have to isolate the variables, which means standardizing the whole operation.
You got it. And to do that, they define what they call the standard mixer duty cycles, or SMDC.
Okay, so these are like the defined chapters of the truck's workday.
That's a great way to put it. There are 4 phases, and they're based on standards like ISO 18868. They basically cover the entire working life of a mixer, making sure every test, whether it's run in Germany or China, is comparing apples to apples.
So it forces the validation team to prove the system can handle everything.
Everything. Maximum power, maximum efficiency, zero power, and super fine-tuned variable speed control.
Okay, let's start with DC1, the feeding phase. This sounds like the big torque shock test.
It is. It's the high dynamic response test. This is when the truck is being loaded with all that aggregate and water.
Right.
So the drum speed has to be kept at 12 RPM or more for about 2 to 3 minutes. Now, think about the physics there. You go from a relatively low inertia to suddenly dumping, 20 or 30 tons of material in a few seconds.
That must create a huge sudden torque demand on that electric motor.
It's immense. The motor control algorithm, the FOC, which is like the brain governing the motor's response, Has to handle these massive sudden torque pulses.
And if it doesn't?
Well, if the control is sloppy, you get two big problems. First, material segregation, because the mixing's uneven. And second, you could get overflow if the motor is too slow to react and maintain speed. So DC1 is all about validating that raw instant power.
Got it. So once it's loaded, the system shifts into DC2. That's the agitation transport phase.
Right. And now it's an endurance and efficiency test. The speed drops way down, usually to between 1 and 3 RPM for the whole trip to the site, which could be 30 minutes, an hour.
So the focus shifts completely from raw power to, what, delicate efficiency?
Absolutely minimal energy use.
Huh.
The motor isn't fighting to mix anymore. It's just trying to maintain flow to keep the material from setting.
And the requirement here must be pretty tight.
It's incredibly stringent. The validation requires the motor to operate consistently in its high-efficiency map. We're talking over 90% electrical to mechanical conversion efficiency. It's all about proving the quality of the motor and inverter design.
Then we get to DC3, the waiting standby phase. You called this the kill shot against the old system's cost.
This is where the electric mixer makes its money. The truck gets to the site, and it might have to wait for half an hour, who knows.
Right.
In DC3, the drum is either stopped completely or just does a short intermittent spin every few minutes. A traditional hydraulic system needs the huge chassis engine, a 400-plus horsepower diesel, to just sit there idling to maintain hydraulic pressure.
Burning fuel the whole time.
Up to 4 liters of diesel per hour, just sitting there.
4 liters an hour, that's
Okay.
just burning money.
It is. The electric system, though, can just shut the engine off.
Hmm.
The 400-volt battery handles everything. So the validation here isn't about performance. It's purely economic. You're just quantifying that massive energy saving.
Okay, and finally, DC4, the discharge phase.
This is all about fine control. The grum goes into a variable reverse speed, maybe 2 to 10 RPM, to push the material out.
And that control has to be smooth.
Perfectly smooth and variable. If it's erratic, you could flood the pump truck chute, or you could stall the delivery. So this phase is all about validating that low-speed torque control and coordination.
So we have these 4 standardized environments, but the source material is really clear that to prove performance, you need data that's way better than what a normal vehicle provides. It says standard CAN bus data is, and I'm quoting, wholly insufficient. Why is that?
Well, when you're dealing with 400 volts, high current, and the super fast switching of the IGBTs, those are the transistors in your inverter, you get incredibly fast electrical signals.
And a ton of electrical noise.
A huge amount of electromagnetic interference, or EMI. Your standard CAN bus data, it might update at, say, 10 to 100 hertz. That is way too slow to capture the details of high-frequency power flow or the little efficiency losses in the inverter.
So you're saying with CAN bus, you might see the average power draw, but you miss the why. You miss the precise mechanisms of energy loss.
You miss everything. The harmonics, the ripple, the exact switching frequency, which is why this playbook mandates a very specific high-precision data acquisition, or DAQ, architecture.
Okay, so what specific high-precision tools are they mandating here? Let's start with the electrical input.
First and foremost, for power analysis, you need a lab-grade high-voltage power analyzer. And the specs on this thing are just, well, they're eye-watering. It has to handle at least 1,000 volts and 500 amps.
But the really crucial specs are the accuracy and the bandwidth, right?
Exactly. The system has to achieve an accuracy of less than or equal to 0.05%. 0.05%.
For a cement mixer, that seems like overkill. Why be so obsessed with that level of accuracy?
Because the entire competitive edge is found in tiny efficiency gains. If your measurement tool is off by even a little, you can't prove the difference between an 88% efficient motor and a 92% one.
And that 4% difference over a whole fleet translates into millions of dollars in fuel savings.
Millions. And on top of that, the bandwidth has to be over 1 megahertz.
A megahertz. And that's to see the high-frequency noise from the inverter switching.
That's it. The pulse width modulation, the PWM, it generates all these high-frequency signals. If you don't capture them, you miscalculate the power factor and the exact efficiency loss in the inverter. The 1 megahertz bandwidth lets you see every single flicker of energy.
Okay, so that's the electrical input, but that's only half the story. You need to know how much of that electricity actually becomes physical work. How do you measure the mechanical output?
That's the second critical tool, mechanical output measurement, using highly accurate torque flanges.
And these have to be placed directly on the output shaft of the motor or the reducer.
Directly on it. It's the point where electrical energy finally becomes mechanical work.
Putting a super sensitive piece of equipment that needs 1% accuracy right on the main rotating shaft in that environment, That sounds incredibly difficult and expensive. Why is that specific placement so important?
Because it gives you the absolute undeniable truth, the electrical to mechanical conversion efficiency. If you measure torque anywhere else, you introduce other variables, gearbox friction, driveline losses.
All the other noise in the system.
Right. By measuring right at the shaft, you strip all that away and you get a pure, verifiable baseline for the motor's performance. It removes all the ambiguity.
Electrical in, mechanical out. So the third measurement is about control. How do they make sure the drum is spinning at exactly, say, 2 RPM during transport?
For that, they mandate high-resolution optical encoders on the drum. The standard Hall effect sensors you see in a lot of EVs just aren't precise enough. They can't catch the tiny microscopic speed ripples.
And the mandate here is a resolution of what, zero point zero 0.05 RPM?
Less than or equal to 0.05 RPM.
That's detecting a fraction of a revolution per minute. Why do you need that micro precision when the drum is only spinning at 1 or 2 RPM?
Because that precision is the proof. It's the validation of why the electric system is superior to the hydraulic one. We'll get into it later. But even tiny speed fluctuations can ruin the concrete. If the engineers can't measure the ripple, they can't tune the algorithm to eliminate it.
Okay, so you have all this high-frequency, high-accuracy data flying around in an environment that's a massive source of EMI from the high-voltage system itself. How do you handle data synchronization so the IGBTs don't just corrupt all your sensitive measurements?
That is a major, major design challenge. The playbook demands rigorous shielding and high-speed synchronization of at least 100 Hz across all the data channels.
So no simple wires.
No. You're often using isolation gateways or, for the most critical sensors, fiber optic cables.
Because fiber is immune to EMI.
Exactly. It's the perfect way to carry that clean data from a high-voltage zone back to the data logger without any pollution. It ensures that when the torque flange reads a peak, the power analyzer sees the corresponding current draw at that exact microsecond.
Okay, with that world-class data foundation in place, the next mission in this playbook is to prove the economic case. You said it before, this whole transition is driven by TCO reduction.
It is. You can have the best tech in the world, but if it doesn't save the customer money, it will fail. Fleet owners live and die by their operational costs.
And the gold standard for proving that saving is what they call back-to-back benchmarking. How rigorous is this comparison?
It has to be scientifically bulletproof. You run the P2 hybrid electric truck against a physical identical traditional hydraulic diesel truck.
Identical meaning?
I mean identical.
Yeah.
Same load mass, same exact concrete mix, same drum geometry, and all the tests are done under tightly controlled ambient temperatures. The source specifies 20 degrees Celsius plus or minus 5.
You're eliminating every possible variable.
So that if the electric truck performs better, the only possible reason is the ePTO system itself.
Let's go back to that kill shot scenario. The DC3 parking and waiting phase, lasting 30 minutes or more. This is where the commercial case becomes just impossible to ignore.
This is the moment the electric system prints money. While the diesel truck is idling its massive engine, burning about 4 liters of fuel an hour.
The electric one shuts its engine off and just sips from the battery.
Exactly. The engineering target here is to prove an energy consumption reduction rate of at least 30% compared to its diesel twin.
30% is a huge technical achievement.
It is, and the commercial reality is even better. Because of the price difference between industrial electricity and high-tax diesel fuel, the source predicts that the actual cost advantage in that idle state often exceeds 80%.
80%.
If a truck spends 4 hours a day just idling on a job site, that completely changes the profitability model for the owner.
So to communicate that kind of saving, you need a standardized metric. And that's where the single cubic meter comprehensive energy consumption, or EFEO, comes in.
Right. This is the financial lingua franca for the construction industry. It's simple. It takes the total 400-volt energy used across the entire duty cycle DC 1 through 4 and divides it by the actual volume of concrete delivered.
It answers the basic question. How much energy does it cost to deliver 1 cubic meter of concrete?
Precisely.
So what's the target? What defines a market-leading product here?
The playbook sets a very, very aggressive benchmark. An efficient hydraulic system is cited at around 1.5 kilowatt hours per cubic meter.
Okay.
The target for this new electric system to dominate the market is less than or equal to 0.5 kilowatt hours per cubic meter.
Wow. That is a threefold improvement. You're slashing the energy cost by 2/3. For a fleet of 50 trucks, that ROI must be almost immediate.
It completely justifies the higher initial price. And the efficiency story doesn't stop there. The system also has to prove its regeneration efficiency.
This is where that massive, heavy drum basically acts like a giant kinetic flywheel.
Exactly. A fully loaded drum has enormous rotational inertia.
Yeah.
So when you need to slow it down, say, dropping from the high-speed loading phase down to transport speed, that energy shouldn't be wasted as heat.
The electric motor can act as a generator.
Right. It harvests that energy and feeds it back into the 400-volt battery pack.
So how do they quantify if that's working well?
They measure the amount of energy recovered versus the theoretical kinetic energy that was available. The target is pretty tough. The regenerated energy must be at least 20% of the theoretical kinetic energy. Hitting that directly extends the truck's electric range.
Now, I see a potential problem here. Regenerating power back into a battery, especially if that battery is already nearly full, couldn't that cause a huge dangerous voltage spike on the DC bus?
That's the critical engineering hurdle.
Okay.
Absolutely. If the DC bus voltage goes over the max tolerance, you can instantly fry the supersensitive IGBTs in the motor controller. It's an expensive failure.
So the battery management system, the BMS, has to be incredibly smart.
It has to do two things perfectly. First, it has to recognize the state of charge. The SOC increase instantly. And second, it has to manage that DC bus voltage to keep it in a safe range.
What if the battery just can't absorb the energy fast enough? What's the hardware safety net?
If the high SOC is going to cause an overvoltage, the system has to use a protective measure called a brake chopper.
A brake chopper. Okay, explain that. What is it doing?
It's basically a smart, automatic safety valve. It's a parallel circuit with high-power resistors. If the BMS senses the bus voltage is about to hit the red line, the chopper instantly diverts that excess electrical power into the resistors.
Where it's just burned off as heat.
Harmlessly dissipated as heat. It protects the very expensive motor controller from being destroyed, guaranteeing safety even when the battery is at 100%.
So we've proven the TCO benefits, but now we move to what might be the most important part of the pentagram, quality.
If the concrete is garbage, none of the energy savings matter one bit. Not at all. The quality of the final product is the customer's #1 concern. You can't tell a construction firm, hey, sorry your $10,000 truckload of concrete is ruined, but look, you save 50 cents on electricity.
Right. So to prove the concrete's integrity, the playbook relies on the washout test. This sounds like a physical autopsy of the batch.
That's a good way to describe it. It's the most authoritative physical test in the world for verifying homogeneity. It's pretty elaborate and time-consuming, but it's designed to catch any segregation.
Okay, walk me through it. Where do they take the samples?
They take large samples, at least 10 kilograms each, at two very specific points during the discharge. One early on at 15% of the total volume, that's the front of the batch, okay, and another one late in the process at 85% of the total volume, the rear of the batch.
And what do they do with these front and rear samples?
They're wet sieved. They're literally washed to separate the fine materials, the cement paste and mortar, from the coarse aggregate, the stones and gravel.
Yeah.
They compare the composition of the two.
The acceptance criteria here must be incredibly tight.
They are. There are two core metrics. First, the coarse aggregate content deviation. The difference in stone content between the front and rear samples has to be less than 6.0% by mass. Any more than that means the heavy stuff is settled out, a clear failure.
And the second metric is even harder to hit, I imagine.
It is. It's the mortar density variation coefficient, or CV. This has to be controlled to an extremely stringent 0.8% or less. This metric is a direct reflection of the consistency of the water-to-cement ratio throughout the entire load,
And why is that so critical?
because that ratio determines the final strength of the concrete. If your CV is high, it means the front of the load might be weak and watery, while the back is dangerously stiff and dry. A CV below 0.8% is the hallmark of a superior, consistent mixing process.
And this level of consistency, this is directly tied to the electric system's big advantage, what you called electric decoupling.
This is the core engineering difference. The big problem with old hydraulic mixers is that the drum speed is tied to the chassis engine's RPM. So when the driver brakes or accelerates or shifts gears, the engine RPM fluctuates like crazy. And because the hydraulic pump is driven by that engine, the drum speed fluctuates right along with it.
So the driver, just by, driving through a city, is unintentionally degrading the quality of the concrete.
Exactly. The mixing is inconsistent. The electric solution completely solves this. The ePTO system is powered by the battery, and it uses its own dedicated motor controller to hold a perfectly steady speed no matter what the chassis engine is doing.
What's the target for control precision to prove that advantage?
The validation target is ruthless. Drum speed fluctuation must be controlled to plus or minus zero point 0.5 RPM, even if the truck is lurching and shifting.
And the internal engineering goal is even tighter.
They aim for plus or minus zero point 0.3 RPM. Hitting that near-perfect constant speed just eliminates the mixing volatility that plagued the old systems.
Beyond just holding speed, the system also has to be smart enough to handle different types of concrete. The source mentions low slump and high slump mixes.
Yeah, it has to be adaptable. A dry, low slump mix, like a high-strength C60 grade, is really stiff. It needs a huge kick of torque to get it moving from a standstill. The motor has to prove it can deliver that.
And on the other end,
A very wet, self-compacting concrete is the opposite problem. It's very fluid, and if you spin it too fast, you get centrifugal segregation. All the heavy aggregate gets flung to the outside wall.
so the system needs to have logic built in to prevent that.
Right. It has to be smart enough to automatically limit the maximum speed for that type of mix. It's essentially programmed to respect the physics of the material it's carrying.
And what's the final check on that adaptability?
The slump loss criterion. Slump loss is a measure of how much the material has stiffened up prematurely. After the whole trip and discharge, the slump loss has to be minimal, less than 30 millimeters or 10%, whichever is smaller.
Which proves the system's gentle, optimized mixing kept the concrete in perfect condition.
Exactly, which means easier pouring and less rework on the job site.
Okay, we've validated efficiency and quality. Now we get into the scenarios that really define a product's reputation. Performance under extreme stress. The source material says reputation is built on how a product handles its worst day, not a normal one.
Absolutely. These robustness tests are non-negotiable insurance policies. If your equipment fails during a critical operation, the financial hit for the customer is catastrophic. You have to validate the system's absolute boundaries.
And the most dramatic test listed here is the full load slope restart. The setup for this sounds brutal.
It is an absolute beast of a test. You have a fully loaded truck, 12 cubic meters, that's almost 30 tons of concrete.
Okay.
The truck is parked, static, on a 30% incline, a really steep hill. And then the crucial part is they wait for at least 5 minutes.
By the way, what does that do?
It allows the concrete to take advantage of a property called thixotropy.
Thixotropy.
Yeah.
Okay, break that down for us.
It just means the material gets stiffer, it gels when it's left undisturbed. On that steep slope, gravity causes the whole mass to slump backward in the drum, compressing and stiffening against the blades at the low end. This creates the maximum possible static resistance for the motor to overcome.
So it's the absolute worst-case scenario for torque demand. The motor has to break that static bond and lift the entire load.
All without rolling back. The pass criteria are simple. It has to restart on the first try, with no exceptions. No overcurrent alarms, no torque limits kicking in, and this is critical. The drum can't roll backward more than 5 degrees.
That demands massive instantaneous torque right at zero speed.
A huge validation of the whole power delivery system.
Now, in the real world, sometimes things just get jammed. That brings us to stall and overload protection. How fast does the system have to react to a physical jam?
Rapid identification is everything. You have to protect the expensive components. The validation proves the system can identify a stall, which is defined as zero speed, but with current draw way above a certain threshold, and get into protection mode fast.
How fast?
The hard target for stall identification time is less than 1 second.
A second sounds fast, but for an electric motor under that kind of stress, that's an eternity.
It is. A sustained stall can burn out the motor windings. So once it's identified, the system has to immediately start the anti-jamming logic.
Which is like a rocking motion.
A high-frequency alternating reversal. It uses mechanical impulse to try and break the jam free. It's a critical safety feature.
Okay, moving from mechanical stress to environmental stress. The thermal management test, simulating a peak summer day.
This is all about endurance. The test involves continuous non-stop operation through multiple full-duty cycles feeding agitation discharge for at least 4 hours straight.
And it all has to happen inside a 40 degrees Celsius environmental chamber.
To simulate the absolute worst high ambient temperatures.
What are the thermal limits? What's the red line for the components?
For the motor, the winding temperature has to stay below 155 degrees Celsius. But the playbook is very clear that just hitting that limit isn't good enough for the final product validation, the PV.
Why not? If it's below the limit, it's passing, right?
Technically, yes. But the engineering team has to build in a critical reliability buffer. The PV requirement mandates maintaining a minimum 10 degrees Celsius margin below that absolute thermal limit.
So it shouldn't run hotter than 145 degrees.
Right. If the system is constantly running right at the edge, at 150, there's no margin for error, no margin for component variation or high altitude or just degradation over the life of the truck.
That 10-degree buffer is the insurance policy against future customer complaints and warranty claims.
It's the difference between a system that technically works and one that is genuinely robust. It's non-negotiable for commercial release.
Okay, so the system is efficient, it makes good concrete, and it can survive extreme conditions. The last 2 points of the pentagram deal with the human element, comfort, and most importantly, safety.
Right, and with 400 volts and powerful computer controls, you have to apply the absolute highest safety standards. Let's start with the big commercial advantage, though. Noise, vibration, and harshness, or NVH.
Traditional mixers are just famously loud. They're disruptive, which means they can't always work when they need to, especially in cities.
Exactly. A traditional system can generate 85 to 90 decibels during discharge. That noise is often the single biggest reason they can't get permits for night work in urban centers. The electric system, with the engine off, just fundamentally solves this.
What's the actual NVH target they have to hit for this silent operation?
The required noise level during discharge has to be less than or equal to 72 decibels. That is a massive reduction. It completely changes the environment for the crew and for anyone living nearby.
But the electric motor itself, it generates its own high-frequency vibrations. Does that introduce new risks?
It does. There's a risk of structural resonance. The high-frequency harmonics from the motor's PWM switching could, in theory, line up with the natural frequency of the big, thin-wall drum or the chassis.
And if that happens, the vibrations could be intense.
Intense enough to cause metal fatigue or even shake high-voltage connectors loose.
So how do you test for that and make sure you're avoiding it?
You do a full-speed scanning test, you run the drum through its entire speed range from 0 to 14 RPM, and you have accelerometers monitoring key structural points. You have to prove that your main operating speeds are far away from any of those critical resonant frequencies.
All right, now for the ultimate non-negotiable, functional safety, following ISO 26262. The consequences of a failure here go from being inconvenient to being potentially fatal.
This is the hard line that protects lives. The number one core hazard for a cement mixer is unintended rotation. Imagine a worker is cleaning the chute or even doing maintenance inside the drum, and the motor just kicks on.
That's a horrifying scenario. What kind of safety rating is required for that?
That hazard is classified as needing an ASIL C or even ASIL D rating. Those are the highest automotive safety integrity levels. ASIL D means you need a near-zero probability of a catastrophic failure that could kill someone.
And what protection mechanisms have to be verified to get to that level?
It's all about multiple redundant safety layers. You have high-voltage interlocks, or HVILs, that de-energize the system if anyone opens a panel. But more importantly, you have to verify the human-machine interaction logic. For example, opening the discharge chute cover has to send redundant signals that make it impossible for the drum to rotate.
Even if the main software has a glitch.
Even then. And the emergency stop response time has to be under 200 milliseconds.
Wow. And speaking of harsh environments, these trucks get a high-pressure washdown every single day. How do you maintain high-voltage safety in a wet environment?
Yeah, water, cement dust, corrosion.
Yeah.
They're all unavoidable. And they all degrade electrical insulation over time, which increases the risk of a short circuit.
So what's the insulation target they have to meet?
Basic regulations might only require 100 ohms per volt of insulation resistance. But this engineering playbook mandates a much stricter OEM standard. Insulation impedance has to stay above 500 ohms per volt.
That's a 5-fold safety buffer.
A critical safety buffer for long-term reliability. And that integrity is constantly monitored by insulation monitoring devices, or IMDs. The validation has to prove the IMDs not only report correctly, but that they execute a protective shutdown the instant that threshold is breached.
Finally, we get to the hard gate criteria. This is where you go from proving the design works, which is design validation or DV, to proving you can build it reliably at scale, which is product validation or PV.
Right, and this gauge system just eliminates all ambiguity. During the DV phase, engineers have a little bit of leeway, maybe a 10% fluctuation is okay on some non-critical metrics while they're tuning things.
But PV is the final exam.
Is the absolute final check, and the rule is simple. Any critical indicator fail during PV means an absolute stop. The product is prohibited from going to regulators or customers.
And there's an even earlier checkpoint.
Yeah, if a critical indicator fails 2 or more times during the DV phase, the team has to stop and hold a mandatory design freeze review. They're forced to fix the fundamental design flaw instead of trying to just tune their way around it.
It's a system designed to prevent a flawed design from ever getting close to production.
It is. And it all culminates in the one-page release decision. It's a summary for management. That page has to show every single core metric, energy, uniformity, control, thermal, safety as a clear pass. If that page isn't clean, nothing ships.
So we've built this incredible engineering success story defined by these tight metrics and hard gates. Now, the final step. How do you translate all this dense technical data into commercial language that wins regulatory approval and closes fleet sales?
Well, before you can even talk to a customer, you have to finalize the system's integrity. You have to address all the known historical points of failure, what this playbook calls the PV risk kill list, or the EC killers.
The EC killers, I like that. So what are the top system killers they have to make sure are dead and buried?
The number one killer is mixing uniformity CV fail. This is what happens when engineers get too aggressive on the energy-saving targets. They calibrate the agitation speed too low during transport, and they accidentally sacrifice the quality of the concrete.
So they have to prove the CV target is met even with the super efficient calibration.
Exactly. The second killer is slope restart torque fail. This is often because the torque limits in the software are too conservative. The engineers model it in the lab, but they fail to account for the real-world physics of fixotropy and gravity on a 30% slope.
They have to go back and validate it with a higher peak current draw.
Right. The other three are pretty straightforward. Insufficient thermal coverage, passing a peak power test, but failing the 4-hour endurance test.
They didn't design in enough cooling margin.
Right. Fourth, stall recognition time being too long. If the anti-jam logic is too slow, you risk breaking things. It has to be under 1 second. And finally, SOSCI feedback credibility. The BMS not correctly managing the regenerative energy. All 5 have to be formally signed off as killed.
Once that internal house is clean, you move to the Q1 strategy, regulatory readiness. How does this data turn into answers for government bodies?
The Q1 strategy is all about preemptively answering the 2 big questions a regulator will always have. Did you compromise safety or quality for efficiency, and can you prove your claims?
So if the regulator asks, did you sacrifice uniformity for energy saving?
The answer is backed by hard data. No. Our system's electric decoupling advantage was confirmed by a 3-segment washout analysis. Our motor density variation coefficient is strictly controlled to less than 0.8%, proving consistency was maintained.
And for the economic claims, is your energy claim verifiable?
Yes. Our metrics are based on the complete standard mixer duty cycle and validated with a high-accuracy DQ architecture with back-to-back comparative data against an identical diesel truck. The data is irrefutable.
And that makes the regulatory process pretty airtight. But the final piece is the Q2 strategy, customer value translation. How do you sell engineering specs to a construction business owner?
You never, ever sell a specification. You sell a business advantage. Take the noise reduction, the 72 decibel target. You don't sell, it's quieter.
You sell.
You sell more working hours and fewer complaints.
Because if a diesel mixer is banned by noise ordinances after 7 p.m.
The electric mixer gets an extra 3 or 4 hours of billable night work. It can completely change the ROI on the vehicle.
Okay, what about the quality control? That CV of less than 0.8%.
That translates to every single truckload is perfectly consistent, which reduces segregation and eliminates rework risk. You're selling predictability. You're selling reduced liability.
And finally, the extreme robustness, the slope restart and anti-stall features.
You translate that as, you won't have a truckload of expensive, time-sensitive concrete stuck on a job site, disrupting the entire construction schedule. You're selling uptime and risk mitigation. Those are the most valuable things in the construction industry.
And this whole intense effort can't be a one-off. The final goal is to build a platformization strategy.
This is the real long-term value. The goal is to make sure all the hard work from this first deep dive can be leveraged. The entire DVPV framework, the risk checklists, the DAQ requirements, the source estimates 60 to 70% of that work can be turned into 100% reusable modules.
So when they design the next truck with a smaller barrel or a different motor, they don't start from scratch.
They perform recalibration, not rewriting. The core control logic, the safety mechanisms, the verification methods, all of that is frozen and trusted. They only need to adjust specific parameters, like torque limits and thermal coefficients.
And the tangible business benefit of doing all that.
It's all about time to market. The goal is to reduce the DVPZ timeline for all future versions of the truck by at least 30%. They can rapidly deploy new, validated products while maintaining the absolute highest standard of quality and safety.
This deep dive has really shown us that electrifying something like a cement mixer is so much more than just swapping a battery for a fuel tank. It demands this exhaustive engineering playbook.
A playbook that defines success through these structured gates and non-negotiable quantitative data thresholds across that entire pentagram of performance.
We saw how you need precision down to 0.05% to validate that TCO advantage of zero point 0.5 kilowatt hours per cubic meter.
And how that relentless testing under extreme stress, from the thixotropic force of a full-load slope restart to a 40-degree continuous thermal cycle, is the only way to build a reputation for real robustness.
And the ultimate discipline lies in those safety requirements. Proving you've eliminated a hazard like unintended rotation requires acile de-rigor and that extreme 500 ohms per volt insulation target for a wet environment.
The source material ends with this really powerful internal summary of the engineering mindset you need for this kind of work. It says, the type approval test is not to prove how great you are, but simply to confirm that you are not out of control.
That is a profound statement. So for you, the learner, think about how this structured, data-driven approach applies to your own work. What hidden engineering gates, those non-negotiable thresholds for safety, quality, and cost, exist in the products you use every day or in the processes you manage, even if you can't see them?
Because every reliable piece of technology we trust is built on the silent discipline of a ruthless engineering playbook, just like this one.
It's the silent discipline that ensures these systems deliver safely and reliably every single day. Thanks for diving deep with us. We'll see you next time.